Antioch College, the basics of photovoltaics and geothermals and how we utilize them. Antioch College is home to many a person, myself included. One of the reasons I am proud to be an Antiochian is because of the collective efforts of the college to be more environmentally friendly. We owe it to ourselves and the planet we live on to attempt to alleviate some of the damage our species has done in the past. We have a solar array, a geothermal plant, a sustainable practicing farm, a recycling and composting program, and various smaller endeavors in and out of the classroom. In this presentation, we are going to talk about the basics of solar, or photovoltaic energy, and geothermal heating, and how we use them here at Antioch. We'll start with some background and basics of photovoltaic energy. In 1839, Antoine César Becquerel first discovered the conductive properties of certain substances to produce electricity from light. William Adams and Richard Day built the first solid photovoltaic device out of selenium in 1876. In the early 20th century, Albert Einstein labeled light energy as photons, and in the mid-20th century, Bell Laboratories were able to create a more efficient solar battery. The lab built it from silicon, which is still widely used to build solar cells. Silicon is the most commonly used semiconductor today, as it is the second most abundant element on the planet and is readily available throughout the world. It is also relatively ecologically friendly. Other semiconductors used for photovoltaics include germanium, selenium, gallium arsenide, gallium phosphide, indium phosphide, cadmium sulfide, cadmium telluride, and copper indium diselenide. The first photoelectric models were extremely expensive compared to natural gas, so their use was very limited, at first only a commodity. NASA's development and encouragement promoted the evolution of the solar model, making photovoltaic systems more efficient and financially feasible to produce and use. The photovoltaic cell itself has little in the way of maintenance needs, is silent and easy to install, and has very low exploitation costs, making it an ideal energy source, particularly for areas that have little to no access to the grid. Solar cells are made of semiconducting materials, primarily of crystalline and thin films. Models vary in light absorption and energy conversion efficiency. The cells are like direct current generators, but powered by solar rays. Each singular cell produces less than 1 volt, approximately 0.5 volts. It takes several connected cells to produce a usable amount of voltage. The cells are interconnected to form panels, which are then connected again to form an array. The top layer of the cell is a matte transparent glass, which cuts down on reflection and allows more light to pass through. 2 layers of silicon are placed between conductive materials. The top layer, or the N-type layer, has extra electrons. The bottom layer, the P-type layer, has extra spaces for these electrons. Where these 2 layers meet is called the p-n junction. Electrons can pass between this junction, leaving a positive charge on one side and a negative on the other. When a strong enough photon hits the silicon shell with enough energy, an electron is knocked from its bond in the N layer and is drawn to the negative side, while the positively charged particle, or hole caused by the vacant electron, is drawn to the positive side. The mobile electrons are drawn to thin metal strips at the top of the cell, and from there they flow through an external circuit before returning through the aluminum sheet on the back of the cell. Electrons are the only moving part of the cell, and they return to where they came from, filling a hole that was created when hit by the photon. Solar energy can be used in one of 2 ways, in a grid-tied system or an off-grid system. The grid-tied system setup typically runs from the array to the inverter to the electric box, from which we can use the power on our loads. A load is anything that draws power, like a light bulb, a computer, or your TV when you watch Netflix. A net meter is put into place for the utility company to see how much energy you are putting back into the grid, if any, and how much you are using. From the net meter, everything runs back into the grid and ultimately the power plant. The major drawback to this system is that if the grid goes down, like in a power outage, then the system also loses power. The off-grid or standalone system is set up to be independent of the grid. The array connects to the system in much the same manner, but instead of tying into the grid, it relies on a battery bank. The major drawback of this system is that the cost is much higher because of the battery bank, and depending on what kind of battery is used, disposal can be very difficult. New technological advances like Tesla's new batteries are much more environmentally friendly, but the costs are still extremely high. Switching gears, using geothermal heat is hardly a new advancement, just more modernized. Our ancestors lived in caves because they stay warmer in the winter and cooler in the summer. There's a reason why the Hobbit home is supposed to be so cozy. Geothermal energy is the creation and storage of heat energy in the ground. Conduction and convection are the two main forms of heat transference that occur within the Earth's crust. We use the convective heat created in the abundant groundwater flow through fractured rock to transfer heat to the surface. This heat is referred to as the hydrothermal resource. The heat found in shallow depths of the Earth's surface is extracted and stored by heat pumps for homes, now a widespread and common system for homes and buildings throughout the U.S. Ground temperatures below frost level remain pretty constant at about 55 degrees Fahrenheit. Typically, in an enhanced geothermal system, we drill anywhere from 50 feet to hundreds of feet down to put in pipelines and loop fields. The pipes transfer the thermal energy from the earth up to the surface and our buildings. In the summer, this means we can gather cool air, and in the winter, warmer air, thus regulating temperatures in enclosed environments. With these basics to be kept in mind, we'll switch to discussing Antioch's usage. Our major solar array is the 1 megawatt array found on South Farm. We also have low-impact land care systems set up in our sheep flock, which rotate from section to section, keeping down the grass levels and ensuring little need for fossil fuel-run lawn equipment. One of our dorms, North Hall, is run off its own rooftop solar array. The farm has a couple different uses for solar, including but not limited to a solar-powered fence to protect our chickens and ducks, and a solar-lit coop to extend egg-laying hours in the colder months. As I said previously, Antioch's South Farm solar array is a 1 megawatt system made up of 3,300 panels designed to offset the energy required to run the central geothermal plant, which is located just behind the Arts and Sciences building. It produces 1,200,000 kilowatt hours a year and runs directly to the plant itself. Over a 25-year plan, it should save the college $400,000 in energy costs. To put it into perspective, the size of this array could power 120 houses. Real-time usage is displayed on North Hall's dashboard screen. Our central geothermal plant heats and cools North Hall, the Wellness Center, and the Arts and Sciences building. It has 150 boreholes drilled 300 feet deep that transfer thermal energy from the earth to the surface, and a compressor staging that optimizes efficiency and diversity of the buildings it connects to. The plant can simultaneously heat and cool water, and its variable drives are set to ramp flow up and down based on the heating and cooling demands of each building. It offsets 2,900 tons of carbon dioxide per year and saves the college around $400,000 per year. Here at Antioch, we utilize photovoltaic energy and geothermal heating to lower our school's environmental impact and to set an example to other institutions and people. Our ideals push us to fulfill Horace Mann's famous saying, "Be ashamed to die until you have won some victory for humanity." This presentation is brought to you with goodwill by 2 Antiochian alum who wish to remain anonymous, as well as the wonderful Antioch facilities. For more information on photovoltaics, there is an excellent online resource at pveducation.org, and geothermal basics can be found in our government's Department of Energy site. There is a copy of this script provided for those who want it or need it in a database. Thank you very much.